decision-making process?
What?
Never mind, you started.
Okay, so I'm going to start with the row sheet first. So I'm going to pass the row sheet around. I forgot about the row sheet last time. I printed it out on both days, and on both days I forgot to give it to you guys. It's just clerical stuff. I just get too absorbed by the lecture stuff, and I totally forgot about the row sheet. All right. So are there any questions about the homework assignment? No. It should not be too difficult. You just have to read the notes again, and make sure you understand the notes, and follow the steps accordingly. It really, this homework, yes, go ahead. What? What is the command to compile? We don't compile in this class, we assemble. And everything, I already sent you a link to the material, so you have to watch it. You basically just have to read it again to find out how to do it. Well, you don't need to refer to the video. You can go to this link here. Okay, let me just show everybody how to do it. And we just need to assemble our first program. So read section 1.5. That's what you need to read. Okay. So we are moving on. Okay. Last time we talked about registers. We also talked about binary numbers. So in this class, I will not ask you guys to come up with the logic gate equations for the half adder, the full adder, and stuff like that. It's still kind of interesting stuff, especially if you're on the track to electrical engineering or computer engineering. So that stuff is actually interesting. And the significance of that whole discussion was, as I said already many times, is we translated something from the arithmetic perspective down to the logic gate perspective. Okay, so that translation itself is the significant transition because we are no longer talking about addition and subtraction. We are now talking about AND gates, OR gate, and NOR gates, but not gates. And that makes it kind of interesting because now we know how to implement a computer using these logic gates. If you have taken some electronic classes, you can actually get set the 74 HC jelly bean parts and just wire up a bunch of things and make your own like 4-bit adder, and you can hook it up to LEDs, so the result will be shown by LEDs, and you can flip switches as the input. But you can do it. You can actually make your own adder using what we talked about last time. So obviously I will not ask you in the first exam to come up with a circuit board that can do like a 3-bit adding. But it would be fun. It would still be fun to do it. If I could do it, if I had the time to do it, I would.
Well, you have the time to write operating systems. You could write a 3-bit addition process.
True, but it's more fun to write a real-time operating system. And these days you can write it, you can actually use those blindingly bright LEDs. That will make, oh, okay. Alex, this makes a great project for the computer science club. Can you remember that?
Actually, over in the
electronics
departments over there, they have the LED
7-segment display.
Yeah, exactly.
Yeah, as I said, I don't like anything other than base 2, so binary is good. We don't need. Have you guys seen those watches or clocks that are binary? Yep.
I look like.
Yeah, well, they're just like regular watches, except they're only like bit patterns. So they have 1-bit pattern for the hour, 1-bit pattern for the minute, and 1-bit pattern for the second. So there are still 24 hours a day. They did not change that. There are still 60 minutes in an hour, and there are 60 seconds in a minute. But from 0 to 60, instead of using a base 10 number, they represent it using 6 bits. So there are 6 LEDs corresponding to, let's say, the seconds. And they use, just LED on and LED off to represent the second, the number. If it is the 30th second, it would turn it, on and off accordingly.
Can we Google to find how you look like?
You can do it later. But that will make an interesting project. So what we'll do today is we'll talk about memory access. Because last time we talked about registers. Registers are great because they can keep up with the computation power of your processors, but they have one downside. There's not a whole lot of registers. So we need memory in order to store programs and store the data and stuff like that. This module does not even talk about why we need memory, because that was discussed already when we talked about registers. It starts off with the actual implementation of the memory subsystem of a computer. And it starts off with a description of a memory chip. Without going into hardware details, because this is not a hardware class, the main memory of a computer is usually implemented by multiple memory chips. This is getting back to very primitive computers and not your Pentium processor or the Pentium motherboards, which are far more complicated than what I'm describing here. The external interface of a memory chip consists of the following. In other words, if you look at the interface from the outside, a memory chip has these following interfaces. It has a bunch of address lines, it has a bunch of data lines, it has one single read-write line, and it has one single chip select line. Okay? So, how do we use all these lines? The pins corresponding to the address lines are input pins. Each pin accepts a binary input, which means it is either a 1 or a 0. And in this case, it's usually high means 1 and low means 0. The address pins together, collectively, can specify an address on the chip itself. If a memory chip has A0 to A9 as address pins, then it can specify locations 0 up to location 511 in decimal, or if you prefer the binary representation, I use 0B as a prefix for binary numbers. So it becomes 0B and then followed by 10 zeros, and then the upper or the highest address will be 0B followed by 10 ones. Is that okay so far? So every memory chip has a whole bunch of lines. But from the software perspective, all you have to remember is you can specify a binary number as the address that you want to address. Okay? Any questions at this point? And every memory chip starts from location 0. If I have 4 memory chips, chip number 1 or chip number 0 will have location 0 all the way to location 511. The second chip will also have location 0 to location 511, and so on. So from the chip perspective, each one has memory location 0 to location 511. Each location of a memory chip is an individual quantum to access. In other words, if 0 is an address, if 1 is an address, then each address, it will give me a particular quantum of data. In other words, it is the smallest unit of data that I can get out of the memory chip. In this case, I'm using an 8-bit memory chip. In other words, every time I specify an address, the memory chip can retrieve exactly 8-bit and present it on the data bus for me to read. The data pins of a memory chip must be wide enough to input or output the content of a single location. In this case, in this example, that means I will need 8 data bits, because each location has exactly 8 bits. So I need 8 data lines in order to either input a byte or output a byte. And typically, on a circuit board or on a chip, they're labeled from D0 to D7. D0 would usually represent the least significant bit, and D7 represents the most significant bit. Are there any questions at this point? No questions? Maybe if I can find a dry marker, I can just start to draw the interface to a memory chip. Okay? So we have a whole bunch of address lines. I will label these from A0 up to A9 because I have exactly 512 locations on this memory chip. I have another bunch of pins, which are my data lines. It goes from D0 to D7 because one location is exactly 1 byte. I have one single pin called a read-write pin because I can specify whether I want to use a write operation or whether I want to specify a read operation. A single line is good enough for that because I can either use high to mean read, low to mean write, or vice versa. In other words, it's a binary pin. I'm either specifying a read operation or a write operation. There's no third alternative in this case. The last pin that I want to talk about is called the chip select pin. The chip select pin usually has a prefix of CS for chip select. And this pin is usually active low, but I don't want to get into the hardware details. So let's just say that we can either say the pin is asserted or it is not asserted. In other words, whether the chip itself is selected or not. Are there any questions about the general picture of a memory chip? A very simple one with 512 locations. Each location is 1 byte in this case. How many pins are we talking about without even counting the power and the ground pins? That's all right. As long as it doesn't do it like 3 times an hour, I don't have a problem.
20.
20, yes. Okay, so in this case we have 20 pins so far, and then plus you need the power pin. So power pin is usually called VCC or VDD, and then you have a ground pin to supply the power. And that's a very simple memory chip right here. Okay, it's a very easy to implement or easy to understand memory chip. Okay, but I have not talked about how these pins will be utilized. The next slide should address that. Okay, so now we talk about the MMU. This is what a memory chip looks like. Do you think 512 bytes is a good size, even for an older system? Probably not, okay? So the next question is, how come we don't have, a single memory chip that can implement up to 4 gigabytes of RAM?
We're close. We can get up to 4 gigabits. We have memory chips that can implement up to 4 gigabits now.
But why not 4 gigabytes? What is the limiting factor? The die size.
Yeah.
Okay, there are many physical limitations, and obviously this limitation applies to very very old systems where one chip can only hold 512 bytes, which is also called a 4 kilobit memory chip. The memory of most computers consists of multiple memory chips. In other words, it's okay if one single memory chip can only hold 512 bytes because we can have many of these little chips in the system. Okay? In the most simplistic case, we can assume all memory chips are of the same size. In other words, I'm not even going to mix and match, with certain chips having 2,000 locations, 2048 locations, some chips having 512 locations, and so on. We'll just make an assumption and say all memory chips are uniform. They all have exactly the same capacity. Interestingly, the address pins of all memory chips are tied. This means the A0 pin of all memory chips are all tied electrically together to one single node. Okay? A node is basically one single connection as far as the conductor is concerned. Pin A1 of all memory chips are all connected, and so on. Now, don't you think we have a little bit of a problem now? If all these pins are tied together, and guess what? The same thing also applies to the data pins. D0 of all the chips, they're all tied together. D1 of all the chips, they're all tied together. And the read-write pins are also tied together as well. So we are talking about these pins, this particular pin and these pins, they're all tied together. All memory chips, if I have 16 of these, all 16 A0s are tied together. Yes?
What about VCC and ground?
VCC and ground, that's power, so they're typically also tied together, but you usually have a decoupling cap right next to it from the electrical perspective. But in this class, since we're more focused on the software side, we won't even talk about the VCC and the ground pins. Yep.
So if you've got 8 chips, for what would that be? 16 kilobits of memory? No, 32. What you could do then is set your address and set your And then all you have to do is swap your cable select and your data pins over and over again, and you've got a redundant array of independent RAMs.
Well, we are not after
Faster
redundancy
RAM.
here. Okay, the chip select pin of each memory chip is connected separately to a memory management unit, the MMU. An MMU these days is usually integrated into a CPU, although in certain architectures, the MMU is a chip that is physically separated from the CPU. We're talking about old technology here. In the good old days, the MMU is not on chip, which means you have the main processor, but hanging out of the main processor is another chip, and part of its function is the MMU, is the memory management unit. So that's just the historical aspect of what is an MMU. One function of the MMU, I'm reading this part here, is to figure out which memory chip should be used based on an address. So let's go ahead and think about this. Okay, so I will draw a picture. Let's make a very simple case where we only have 4 memory chips. Each one has 512 bytes. So we have 512 bytes here, 512 bytes here, 512 bytes here, and 512 bytes here. Together, we have how many bytes? We have 2,048 bytes. Okay. The MMU is going to do something that is interesting. This is our MMU, and here's the CPU. The CPU is what your software specifies. In other words, when the CPU says, I want to go to location 600, it is from the software perspective. I want to go to location 600. The question now is, where is location 600? Each memory chip only has 512 locations. So what needs to happen now is a translation. The translation to go from the logical address, okay, in this case, let's just say that the CPU wants to access location 600 in base 10. The MMU is now responsible to figure out, okay, let me see which chip actually has location 600 in the logical sense. And then once it figures out which chip has location 600, it also has to figure out, okay, but which location on that chip corresponds to logical location 600. Okay? So let's see how this can be done. The easiest way to do it, typically this is how it is done, is we name each memory chip from 0 and up. So let's say this is chip 0, this is chip 1, this is chip 2, and this is chip 3. So are we doing okay so far? We use sequential numbers to number the chips. So once we do this, we can now start to say, oh, well, that makes it kind of easy because we can just say that chip 0 will provide logical location, location 0 to location 511. Chip 1, which is the second chip, will give me location 512 to location 1023. And then this will give me location 1024 all the way up to location what? 1535.
One five three five.
And then this is going from 1536 all the way up to 2047. Okay. In other words, these are my logical addresses. Are we doing okay so far? We are stacking up all the memory chips to give us an illusion that we have location 0 all the way up to location 2047, even though each chip only has 512 bytes. So getting back to this example, which chip do you think has our location 600? Chip 1. Okay, the second chip, chip 1. Okay, so the location 600 is probably somewhere around here. Now we have to say, okay, now that we know this chip has that particular location, that means I can hold off chip select of that means CS0, the chip select of chip 0 will be off. It will not be asserted. The chip select of chip 2 will be disabled. The chip select of chip 3 will also be disabled. The only chip that would have a chip select pin asserted is going to be chip 1. Now we tell chip now that we have told chip 1 and say you are the one selected, we have to tell chip 1 which location on the chip we want to access. What is the location on this chip that we want to access? Now we're talking about physical location. It'll be 600 minus 512, so we have 888. Okay, location 88. Okay, so in this case, what do you think will be the bit pattern that has to be on the memory bus? It'll be 64 plus what? 88 in binary is, I think it's 64 plus 16 plus 8. Is that right? That looks right to me. So we have 1, 0, 1, 1, and then 0, 0, 0. And since we have 10 bits, so that means the most significant, that means the 128 is a 0, the 256 is a 0, and there's no 512. This is the bit pattern that we have to produce on the address line. Okay, sorry, some people cannot see it. 0, 0, 1, 0, 1, 1, 0, 0. Okay, so we have 0, 0, 1, 0, 1, 1, 0. Nope, can't see what I... 1 more 0 in the end? That's not 10 bits. I'm still missing something.
You're missing the 0 on the left-hand side. You only have 9 up there on the left.
So I'm still missing 1 on the left-hand side? Okay, this is 64, this is 128, this is 256. I should not have 1 for 512. Because the entire chip only has 512. So maybe it's a 9-bit address, not a 10-bit. So I messed up originally because it only has 9 address lines. So this is my A0, and this is my A8, not A9, sorry. My bad.
When you have to break on when you have to break on 64, 16, 88. I mean, for the 88, why you have to break on 64, 16, 88?
Because I want to do the base 2 conversion.
That's base 2.
Yeah. These are all powers of 2, and that's how I convert a number to base 2. When I don't feel like punching it in on a calculator. Okay, so are we doing okay so far? So now we now finally have a way. Okay, when software wants to access logical location 600, the MMU goes through all the calculations and it figures out this is the address on the chip itself, and we want to use chip 1 in this case in order to access that location. Are we doing okay with the translation process? How we translated from a logical location of 600 to the physical location of 88 on that chip, and also which chip we want to access. Now, in reality, sometimes you can have memory chips of non-uniform sizes. In other words, you can have memory chips of different sizes, and it will still, in the end, work out. You just have to know, where's the boundary between the chips. So it will still work out. Some MMUs are smart enough to actually do that as well. And I have another example here. So in other words, if you don't want to copy whatever is on the board right now, there's another example in the notes. It's just not the same. Okay. Any questions at this point? Yep.
I'm wondering if you only have one D set, how do you do long-term storage? I mean, wouldn't every time you use this chip, you lose all the data you have stored on that chip?
Well, okay, so you're talking about the differences between DRAM versus static RAM. Is that right? Okay, we can assume that we are using static RAM at this point, so you don't need to refresh the RAM chip. Okay, I have an analogy later on, that will describe exactly, how a memory cycle works. So maybe that will be helpful. Are there any questions on this page? How we can calculate which chip to use and what is the address that we need on the address bus? Let me give you an analogy nonetheless, okay? Because I can see from the facial expressions that an example may be helpful. Okay. So let's just say that let's say you four here, each one is a memory chip, okay? And each one of you has a binder, okay? So all four of you have binders, and all the binders are of the same size. Each binder has exactly 512 pages, okay? So collectively, how many pages do we have?
2047.
2048 pages, right? Okay. So let's say I'm the CPU and I'm running a program. Okay. According to the program, I need to access page 600. Okay. So I'm using exactly the same example as on the whiteboard here. Page 600. Obviously, I cannot ask any one of these memory chips and say, do you have memory or do you have page 600? Because none of them has page 600. So the MMU, which is between me and the memory chips, will do the translation. The memory chip, the MMU, will basically say, okay, I understand that we have 4 memory chips. Each one has exactly 512 pages on one side. And on the other side, the CPU wants to access location 600. So it will go through the calculation. In other words, the MMU is the one that will say, okay, you are chip 0. So I will see your page 0 to 511 as actual location 0 to 511. Your chip 1, I will see your location 0 as logical location 512. And you will have all the way up to 1023, location 1023. So the MMU is doing all this translation. Is that okay so far? So when I need to access location 600 from the CPU's perspective, the MMU will take that from the CPU and go, okay, location 600, that means you have the page that the CPU wants to access. But on your binder, it is not page 600 because you only have page 0 up to page 511. So the MMU would also do the translation and say, from your perspective, memory chip, it is page 88. Okay? Now, the magic of this whole thing is other than the chips select line, which are individual to each memory chip, every other line are shared. That means as the MMU, I can scream out everything else to all 4 chips. In other words, I can say, I want to access location 88. All 4 chips are listening to that request to access location 88. But then, and I can also specify a read or write operation, but when it is time to specify who gets to do it, I will say, guess what? You are the chosen one. Okay? And the other 3 chips cannot hear that because the chip select line is specific to a chip. Okay? And that's how it works. Okay? And that's why we can share the address lines with all the chips, we can share the data lines with all the chips. It's because only the chip that has the chip select line activated or asserted will actually respond to the MMU's request. Yep.
So the MMU is going to actually turn on the chip select for whichever one you're trying to access, or their default is set to on and you have to turn all of them off except for the one?
That's a good question. The question is, does the MMU have to turn it on, or is it by default on, or what? By default, from the memory chip's perspective, the chip select line is only an input to the memory chip. As such, it is what we call a floating line. Okay, if the MMU does not do anything, it's just floating, which is a bad thing because it can be high, it can be low, it can be somewhere in between. The MMU is the one responsible to drive the chip select line. So normally, the MMU will drive the chip select line to all chips and say, none of you is selected. Don't talk to me. Okay? But when it is time to ask for the content of one page, then the MMU will assert one and only one chip select so that that particular memory chip can report the content on page 88 in this case. Is that making any sense? So the MMU is the one that is controlling or driving the chip select lines as well as the address and the data lines. Well, the data line can be, sometimes it's driven by the memory chip and other times it's driven by the CPU. So we'll talk about that in the next slide. Yep.
If you write out the number 600 as an 11-digit binary number, you'll see that the chip number is the high 2 bits,
yes,
and the rest of the address is the low 9.
Yep. In other words, you're partitioning the binary number and use the most significant part as the chip that needs to be activated or to be selected, and then use the least significant part as the actual content of the address bus. Yep, that'll work. Okay, is that better? I mean, do you guys feel that you have a slightly better understanding? Okay, so this part here talks about the very itty bitty details of how memory cycles work. A single memory cycle is what the processor, or how the entire system has to go through in order to write a byte from the processor to memory chips, or read a byte from the memory chip back into the processor. The first one is a memory write cycle. If an instruction is to update the content of a memory location, then the following has to happen. Step 1, the MMU computes the chip number and the address on chip, okay, which is what we just did a little bit earlier. The address is latched onto the address lines. In other words, the MMU will drive the address lines, A0 to A8 in this case. It will, excuse me, okay. It will drive the address lines A0 to A9, high. In this case, we have low, low, high, low, high, high, low, low, low. Okay. Now, what is high and what is low depends on the memory chip. Back in the good old days, 5 volt is high and 0 is low. But these days, our memory chips, are lower voltages. Can handle lower voltage. So high maybe 1 point something volts instead of 5 volts. So you have so the address lines are all determined in step 2. And we keep the address lines driven exactly like this for the entire duration of the cycle until we say, okay, we don't need the address lines to be driven anymore. In this case, I use a low on the read-write line to specify a write operation. This is somewhat arbitrary, but I think in industry there's a specific standard that most processors follow. So in this case, a low specifies a write operation. And since this is a write operation, the processor or the MMU is responsible to specify the content on the data lines. Okay, are we doing okay so far? In other words, the processor will say, oh, I want to update location 600 with the new content. Let's specify new content here. Let's say hexadecimal A4. Okay, that's the new content. So that means the processor will be responsible to control the voltages on D0 to D7, the data lines. In this case, the data lines will be driven to high, low, low, high, low, low. This being D0 and this being D7. Okay? Are we doing okay so far? So first we specify the address lines, then we specify the read-write line, and then we can specify the data lines. The order does not really matter. Okay, you can change the order of these 3 operations any way you want, because guess what? Nobody is listening. Okay, because I can scream all day long. The 4 of you do not pay attention until I say, okay, you pay attention. Then you will go, oh, okay, I better pay attention. The address line is this, the data line is this, and this is the operation. I know how to do that. Okay, but until I assert a chip select line, all the memory chips are just listening to the traffic, but nobody is doing anything. Are we doing okay so far with this model? Okay, question? No? Okay. Now the chip select line is asserted to select one and only one chip. So only one chip will have the chip select line asserted, which basically is the MMU telling that chip and say, pay attention. Now when the chip pays attention, there are several things that it has to do. The first thing, and this is completely internal to the memory chip. The first thing that the memory chip has to do is to sample the address lines, because remember, the address lines are already being driven by the MMU. Okay, it already has a particular pattern on it. In this case, it has a pattern of low, low, high, low, and so on and so forth. Okay, so at this point, once the chip select line is asserted on that memory chip will just sample the address lines to see which address line is high and which address line is low. That will take up some time, and this cannot be observed by the outside world because it is all happening inside the memory chip. After step 6 is step 7. The selected memory chip will connect the data lines to the location specified, and this also cannot be observed. In other words, it's equivalent to you flipping to page 88. Once you understand I want you to overwrite page 88, it will take you some time to flip to page 88. Once the memory chip connects the data line to the specified location, then the location is overwritten by the content that is already specified on the data line. In other words, you are just overwriting the page, of the content of page 88. That will take up some time as well. So what we have here is everything from step 6 all the way up to step 8 cannot be observed. Okay, we do not know. We cannot use an oscilloscope to find out whether the memory chip is done or not. We just have to say, well, the MMU will just say, I'll give you some time to finish it. Okay, from the time I assert the chip select line, I will say, well, I think giving you 5 seconds should be enough. Okay, so you will spend so you will spend whatever amount of time you need to finish the operation. Hopefully, it is less than 5 seconds. And this is what we call the wait state. Okay, if you buy memory chips, sometimes they will have specifications like wait states. This is what wait state is all about. Okay, how much time the memory chip needs in order to complete a read or a write operation. Now, once the MMU waits for the fixed amount of time, then it will release the chip select line. In other words, I will tell the memory chip and say, okay, you don't have to pay attention anymore, because at that point, I might change the address line and the data lines to get ready for the next memory cycle. So the memory chip will need to be deselected so that it doesn't pay attention anymore while the data lines are, or the address lines are getting changed. And then at that point, the MMU can stop driving the address line. The address line can go floating again, and the memory cycle is now completed. This is a write cycle. This is how we write to a single location on a memory chip. Are there any questions so far?
Do we need to remember all the steps?
The test is going to be open book, open notes, so there's no memorization. You have to understand it and apply it. Yep.
There's a book
There's a book. Yes, what you're seeing here.
right here.
Yes. You can print it out. You can put it on your thumb drive. Yep.
So this is actually what a modern chip is doing at like 1300 megahertz. It's doing that many times a second.
Not quite. That's a good question. The question is, if you buy DDR3 memory these days, they can be specified to go. I think these days can go all the way up to 1600 megahertz, which is actually which is the wrong unit, because it should be called 1600 transfers per second. That's the proper term. No, that's not how it works. Okay, because this will probably take up quite a bit of time. Okay. The reason why DDR2 and now DDR3 can be so fast is because they can skip a few steps. Okay, the memory chips are getting smarter. So what I can do is I can say, hey, Mr. Memory Chip, I want to start reading at location 88. Okay, but I can also tell the memory chip, I'm also interested in the next 8 locations. Okay, so now the memory chip will wait for a certain amount of time to give me location 88, the content of location 88. But at the same time, the processor and the memory they are now synchronized. So I will wait, X amount of time for the memory chip to respond to the first location. So you would tell me what is on page 88. Then I will wait a little bit more time, and you will tell me what is on page 89, without having to go through all this trouble again. And that's why DDR2 and DDR3 are fast, because you don't have to go through all these steps, because the processor and the memory chip can have an agreement and say, I'm starting to read at this location. give me that location and also the next 16 or 8 or whatever number of locations. And from that step on, it is all based on synchronous operation. In other words, I'm assuming you can give me a new location every 2 seconds. So I will sample the data bus every 2 seconds. If there are any mismatches, then I'm in big trouble. Yep.
But that's only for if those next addresses are on the same chip, right?
That is correct. When you do DDR2 and DDR3, this is what they call a burst mode read or burst mode write. They can only happen to a block within the same memory module. So there are restrictions as to what sequential locations you can read sequentially. You can use this particular burst mode of operation. And this also ties into how the cache of your processor works. Because when you fill up the cache of your processor, you're not going to fill it up like 32-bit or 64-bit at a time. Every time you fill up, your cache, it's going to be filled up, using much larger quantities. So it will take 8 read operations anyway to read, into one, single quote-unquote page of your cache. And that's how, DDR2 and DDR3 works. Is based on assumption that you will also need the next so many locations. Might as well read all those locations all at once, so you can save all the time to to change the address line, to reassert the memory chip, and also and all the other stuff that are associated on this page. Now, the DDR2 and DDR3 discussion is completely off topic, so I will not ask you questions about the DDR2 and DDR3 memory. But since you guys asked, I just thought this is the right time to introduce those concepts. Okay. Now, if you have to read random locations, okay, if the MMU comes out and you disable the burst mode, of read and write operations. DDR2 and DDR3 are no faster than conventional memory because you still have to go through all these steps. There are no sequential read operations. And as a result, it doesn't help. Yep.
They're still faster because they run at higher clock rates.
DDR2 and DDR3 run at quote-unquote a higher clock rate, but they are not exactly at higher clock rate. They're basically using both the rising edge and the falling edge of the clock to synchronize the operations. And I think with DDR3, they can also do synchronization between the transitions, and that's why it can speed up the access. But when you are setting up the address line and the data lines and also the chip select line, I believe those operations still have to land on top of the edges. They cannot be like have an edge off. I could be wrong. And DDR4 is out, right? No?
No, but GDDR5 is in.
GDDR, okay.
Only for graphics cards.
Only for graphics cards. Okay. Now, since we are on this discussion here, do you think that algorithms can make a difference in terms of the actual speed of execution time? If you have an algorithm that has a lot of sequential read in memory locations, then you can utilize DDR2 and DDR3 to its maximum capacity because you are always interested in following locations and following locations and following locations. So when you pre-read in burst mode, when you pre-read into the cache, guess what? You're doing the right thing because you will need all that data sooner or later. But if you have an algorithm that has random access all over the place, then it doesn't help anymore. Okay, because the stuff that you read ahead in burst mode turns out to be useless. So that's why the algorithm, if you have algorithms that will do a lot of sequential read, then DDR2 and DDR3 in burst mode will help. Are we doing okay so far? These are extensions to the concepts that we are talking about, but it still relates to all sorts of software and programming issues. Yep.
So an example of that, like burst mode usage, is like the startup, where you specify which programs to start up.
I would say, when you're processing data, if you are using, let's say, Fourier transform or something like that, that you have to read the next locations sequentially, that will, make use of, DDR2 and DDR3 memory locations. When you have programs that are all over the place, this applies not only to data, but it also applies to code. Okay, because both code and data they all live in memory. They all live in RAM. If your program has long sections of code that you just execute sequentially, then the read ahead in burst mode will help. If your program has a lot of branches and every time you branch it goes to a really far away place, then you're quote unquote breaking the pipe, and also the read ahead operation is not of any value because what you just read ahead is not useful. Yep.
And programs that are repeating the same faraway branches repeatedly,
The
help
cache.
L2 and L3 caches help to mitigate that added cost.
Yes, it will. The next slide talks about memory read, okay, which is another type of cycle. But once you understand what is memory write, memory read is really quite easy. Except the only difference is who is driving the data bus. Okay, so in a memory read cycle, the MMU still has to compute which chip is responsible, and what address do we need on that chip. The address is now being driven. In other words, the address lines are now driven by the MMU to specify, okay, I want location 88. The data lines are left floating in this step. Now, this is the difference. This is different from the previous slide because when you are reading from memory chip back to the processor should not drive the data bus. The data bus should be left floating by the processor, and later on it will be driven by the memory chip. And then we can specify this is a read operation, but since we use low to specify a write operation, a high voltage on that line will specify a read operation. And nobody is actually doing anything in the first 4 steps because the chip select is left unasserted on all chips. Yep.
We're doing read, but you say the line is held high to specify a write operation.
Oh, typo. Thank you. I can fix it now, or I can try to remember and fix it later.
Write it down and fix it later.
Can you write me an email? Thank you. The chip select line is now asserted to select one memory chip. Okay, once the memory chip is selected, then it will look at the address bus. The first thing it will do is to look at the address bus. The selected memory chip will sample the address bus to determine what location should be connected to the data pins. Then the selected location of the selected memory chip will connect to the data lines. In other words, the memory chip is now driving the data lines. Okay. The MMU will wait for a certain amount of time. Once again, this is what we call the wait state. So some memory chips are slower. You need to allow more time for the memory chip to complete its operation, and other memory chips are faster, so you don't need to wait as much time. And when the MMU after the MMU wait for a certain amount of time specified by the wait state, then it will go ahead and sample the data lines because on the data line is now the content of the location that the processor wants to read. Is that making any sense? Okay. And after that, the MMU will release the chip select line, telling the memory chip and say, okay, you don't have to pay any attention anymore, don't drive the data line anymore. And then the address lines are no longer driven by the MMU because there's no need to drive the address bus anymore, and the memory cycle is now completed. Okay. Are we doing okay with all the different steps and how they connect? Yep.
So what would DDR2 and DDR3 affect this process? Like how would it affect this?
They would affect this process, because when you specify which location to read, on top of saying that, you're also specifying, burst mode. And I'm not sure whether you can specify the number of following locations to read, but there is a way to do it. Either it is a understanding between the processor and the memory chip, it is always 8, it's always 16 or something like that, or it can be a part of the bus structure. There may be another few lines that can specify how many locations to read after that. So basically you are repeating this step here without having to recycle the other steps. In other words, once you specify all the other steps, the MMU wait for a certain amount of wait state, sample the data line, and then and then you wait for another wait state, and then you sample the data line again. It is understood between the processor and the memory chip that they will have, and there will be another data sample ready in X amount of time. So you're saving all the other steps. You just have to wait, read again, wait, read again, wait, read again. And everything has to be synchronous, by the memory clock itself.
What's in between the MMU and the ALU at this point?
The MMU is only responsible to do address translation. It's responsible to control the chip select lines and stuff like that. The ALU is responsible to actually do all the computations, the 32-bit add, 64-bit add, 64-bit multiplication, and stuff like that.
Between those two block boxes at the moment? Is there a cache that it goes to, or?
This is the very last step. When everything has to go out to the DIMMs, to the dual inline memory modules, they have to go through this process. But before they have to go to the memory chips, internal. All that stuff will happen before the MMU.
Oh, I meant on the read. Does it go to the register straight from that MMU?
The read operation can read straight into an ALU because the Intel processor allows you to specify a memory location as an operand. So it can go straight into the Y shape and feed the ALU directly. It does not have to go through a register first. Yep.
I have a question. What do you mean in line 10 when you say you select memory chip stops driving the data lines?
Okay, it's because the MMU has now released the chip select line. Now remember, in this operation here, when we're reading a single location, after step, let's see here. After step 7, okay? After step 7, the memory chip will continuously drive the data line. In other words, the memory chip will keep screaming on the data line and say, page 88 is A4, page 88 is A4, page 88 is A4. It will keep screaming that, okay? So we need to let the memory chip know, okay, you can stop screaming now, I got it, okay? Because if the memory chip keeps screaming on that line, I cannot start the next cycle. Okay, is that making any sense? Okay. Mm-hmm. Yep.
So, how much data are we talking about can be transferred per memory cycle?
It depends on the number of data lines. In this case,
how many bits?
Yes, that determines how many bits can be transferred all at once.
It's just like one parallel burst, everything at once.
Yep. Mm-hmm. They're all in parallel. What is the width of a DDR2 memory bus these days? I know it's not 32. I know it's probably more than 64. Is it 128 bits now? One transfer is 128 bits? No? Sorry?
I'm pretty sure mine is 64 bit controller, so 128.
128, okay. Are there any other questions about the memory cycles? Memory read cycle and memory write cycle? No questions? Okay. So that's the memory implementation. And now we have cache. Cache is just a discussion here. Cache is a special type of memory that sits between the processor and main memory. A cache can be seen as a special type of what we call associative memory, associating a physical address to its content. Now, usually it's not by every location. In other words, you don't have addressability like single bytes. You usually have a block in this case. When the processor needs to access a particular memory location, it transparently, in other words, in software you do not have any control, it will inquire the cache first. It will ask the cache, hey, do you have a local copy of page 88? If the cache replies and say, yes, I got page 88, then the cache can feed the processor, and that can be done a lot faster than memory. If the cache does not have that content, then something else has to happen, because we have to determine, do we want to throw away something else in the cache in order to get page 88 into the cache? The cache is significantly smaller than the total addressable memory space of a computer. In other words, if you look at processors or computers these days, 4 gig of main memory is not too much. Most computers will come with 4 gigs of RAM these days. How much of cache do we have? Level 3. Okay, we're talking about level 3, which is the slowest of all types of caches. How much level 3 cache can we expect out of a consumer type of processor?
6 megabytes. 6 megabytes.
6 megabytes. Okay, so how does 6 megabyte compare to 4 gigabytes? They're off by several orders of magnitude. Okay, so that means we cannot fit everything into cache. This is a very valuable resource, and we can only have so much because having more cache will increase the die size, and we cannot have the die being too big. Modern computers have multiple levels of caches. Level 1 cache is closest to the processor, and then we have level 2, which is one level out, and then we have level 3, which is the last level of cache. And these days, even the level 3 cache is on the chip itself. Okay, it was not very long ago, back in the 386 and back in the 386 days, that we have external cache memory. If you look at the motherboard, they actually have specific chips to implement cache memory on the 386 motherboard. I think the 486 was the first processor that has internal cache instead of external cache. Can anyone confirm that? No one?
Confirm. Confirm.
Confirmed. It is all recorded. I'll have it notarized. Okay, so we talk about burst memory access here. SDRAM, stands for. Oh, what is SDRAM?
Synchronous dynamic random access memory.
Yep, very good. And the key is synchronous. Okay, synchronous means there's an agreement between the processor or MMU and the memory chip. Okay, they basically will agree and say, in DDR, in the original DDR, they will agree and say, okay, when it is the rising edge of the clock, there will be a data available on the data bus. Okay, and when it's a falling edge, there will be another data available. So when the clock goes up, the processor will read, they will sample the data line and say, okay, I got a byte. When the clock goes down, the processor will assume whatever is on the data bus reflects the content of the next location. When it goes up again, it is the next location. When it goes down again, it is the next location. DDR2 will also fit, a clock or a sample time between the transitions. Okay, between the rising edge and the falling edge, it will also assume that in between two edges, I can also sample the data lines because it also represents the content of another location. So that's why we get the speed of transfer to be much faster than the actual clock speed of memory. When you go into the BIOS, you can actually see the clock speed of your memory bus. It is typically much slower than, say, 1600 megahertz. Are there any questions on this slide? This is stuff that we already talked about.
So, since you can't increase the clock frequency, that's why you just sample at a higher rate?
You can increase the clock speed. It's just that, the clock has to feed to multiple chips, and as a result, you cannot clock it. You cannot change the frequency of the clock chip, as easily, and just, turn it, crank it up. Yep.
Some boards run at 100 megahertz and others at 133 and other various frequencies in between.
Mm-hmm.
How does that affect the rising and falling and the ability to sample at greater frequencies?
Well, let's go ahead and check what is the actual memory bus clock speed, for DDR2 and DDR3. So we just look up Wikipedia. Now this stuff here is definitely off the scope of this class, but since it is closely related to what we are talking about right now, so I'll go ahead and. Okay, so data is being transferred 64 bits at a time with DDR2.
In dual channel, it can be 128.
Right. Okay, so its memory clock rate times 2 for clock for a bus clock multiplier for times 2 for dual rate times 64 bits per transfer divided by 8, which is the number of bytes. So the clock frequency in this case is 100, while the maximum transfer rate is 3200 megabytes per second. So that means, the times 2 here is the key. Basically, okay, the clock is measured from falling edge to falling edge or rising edge to rising edge. But if you can use both the rising edge and the falling edge, you just doubled the number of transitions that you can use. And that's why we have it multiplied by 2 there. And that's DDR2. With DDR3, I think it will fit a sample time between clock transitions. Is that making any sense? No?
So, like if you have a sine curve, then that basically means that you're fitting 2 increments in. Sorry.
Yeah, because a cycle has to be complete. The end has to meet the beginning, right?
No, I just meant a sine curve, like visualizing, right?
Right. So with a sine curve, okay, with a sine wave here, one wave is from here to here. Okay, this is one period. But with a square wave, okay, because the processor uses a square wave, then one clock is from here to here. Without using DDR2, okay, you can. This is one sample time. So let's say on every falling edge you can sample. So this is one falling edge, this is one falling edge, and so on. But if the memory is capable to sample also on the rising edge, now you have suddenly just doubled the amount of transfer that is possible per unit of time, without changing the actual underlying clock speed. Now with DDR3, if I understand correctly, it will also sample between the transitions. So this will also be a time to sample, this will be a time to sample, this will be a time to sample, this will be a time to sample. So that's why we can.
It would sample in the corners.
So
DDR4 would sample in the corners.
It gets incrementally difficult because there's no signal to tell both the processor and the RAM this is the time. There's no edge. There's nothing that can be observed. So this is purely based on the internal timing mechanism of both ends to say that, okay, this is the right time to latch out the data, and this is also the right time to sample. So that timing is really, really critical with DDR3 already the way it is.
Can that lead to memory problems in computers if it's off sync?
If it is off sync, then you can read the content of either the previous location, mistakenly understanding it as the current location.
Right, or writing to the one you just.
Correct. So you can have mismatches of the steps.
Yeah.
That would be bad.
That'd be very bad.
Yeah. Yep.
Scroll down a few more windows working on that page, and you'll see a table of alternate memory clock and I/O bus clock speeds.
Ah, very good. So the I/O clock speed is twice as fast as the memory clock in this case. And this is mega transfer. This is number of transfer. So basically, if you have a clock of 200, you can actually do 800 transitions in this case. But remember, the key is synchronous operation. The clock is there it's basically the drum beat for everybody to sync to the same rhythm. Okay? But between the drum beats, you now need to rely on internal timing to play those notes. Okay? If the timing is off, then these chips will be in big trouble because they will be playing a note at the wrong time. Are we doing okay with the basic concepts, not the details? Yep.
Set of questions, kind of random, but so for hard drive connections, they went from parallel back to serial. I'm just curious, do you think they'd ever do something like that with memory?
They did.
Just go back to serial and just crank it up?
They did. Intel had something called the RAM bus, and it was basically something like that. That stuff is actually fairly high tech. There are several reasons why they go from parallel. PATA stands for parallel ATA, which is what we call IDE. In common terms, But to go from parallel to serial, it doesn't seem to make any sense because in parallel we can transfer more stuff, right? But there are other things that are bad about parallel transfer.
So you have to wait for it.
Well, one thing is you have to wait, but you have to wait for serial transfer as well. The first thing that is bad about parallel is from the board layout perspective. Think of all those poor Taiwanese motherboard designers. Okay, when you have how many lines going parallel from this chip to the other chip. Okay, you have the IDE bus, you have the memory bus, you have the PCI bus, and so on and so forth. They're going all over the place, on the motherboard. The routing, to actually draw a line from one point to another point without two lines actually crossing is hard. That's not easy to do. And when you have like a lot of these lines going across like that, it becomes very difficult to design a board that can operate at high speed. So that's why they went from parallel back to serial, is to make board layout easier, because with fewer lines to route, it is easier to design motherboards. Yep.
Even at such short distances, if the length of those traces is off
Yes.
by even a small amount, because of the speed of light transfer of electrons, you can cause variations in off by 1 bit
Yes.
out of 8 in a parallel transfer.
Yes. But the problem is not only the length itself, it's not just the time itself, it also has to do with the inductance and the capacitance of the lines. If the length of different lines are different, then the inductance and the capacitance of those lines will also be different. In other words, this is a perfect square wave, okay, which is what we want on a motherboard. With inductance and capacitance, it's not going to look like this. It will look more like this. Ring a little bit, ring a little bit, like that. Okay, so depending on how much inductance you have and how much capacitance you have, the shape of the perfect square wave can be way off. Now, what can be way off? What can be worse than way off? Different lines are off in different ways. Okay, that would make it even worse, because now it is really hard to kind of match up all the lines that you need in a parallel bus type of architecture. So that's another reason why they went from parallel back to serial. And that's not just with the ATA bus, it's also with the PCI bus. PCI Express is quote unquote serial, even though you can specify one. Do we have 2-lane PCI Express bus?
1, 4, 8, or 16.
Okay, so they skip 2. But it's for the most part a parallel. It's for the most part a serial scheme instead of a parallel scheme. Okay, so that's a kind of interesting question, but the answer has to do with all these different factors for designing a motherboard. Okay. Then we talk about I/O, or input/output. But we have a full computer now. We have the processor, we have the MMU, we have the memory chips, we have the registers, we have the ALU. We can do lots and lots of calculations. We can, and we can store, everything back into memory. We can take, data from memory, process it, and put the result back into memory. What are we missing here? What are we computing?
We don't know.
Nothing. Right?
Whatever we preloaded into memory.
Yep, that's it. So every time you start on your computer, it will go through all those calculations exactly the same way as before.
Except that it reads from your random number generator that's hardware based and based on radiation from the sun.
Or you can always, just make it read in empty space. So depending on how the data line is floating, you can read some different things kind of randomly. Okay, but without I/O, your computer is useless. Without input and output devices, your computer is useless, because it will just be doing the same processing over and over and over and over again. So the next question is, how does your PC talk to something as simple as, let's say, the keyboard? Okay, these days we use USB, but the next question is, how does USB devices talk to the processor? Okay, in the end, what is going on between those two in order for them to start to talk to each other? So the first thing we want to know is, what is an I/O location? Okay, there are 2 ways. One is called memory mapped I/O, and the other one is called I/O mapped I/O, which is kind of like a redundant name, but it is what it is. Okay, the Intel architecture uses I/O mapped I/O. In other words, I/O devices have their own space to exist. Okay, now that seems kind of strange. Let me go back to one of some of the stuff that you guys already know, or hopefully you have encountered before. This is just an example. So let me see if I can find it. Here, COM1 serial port, IRQ.
COM hardware interfaces.
I want to find out what the locations are, the I/O locations. Maybe it doesn't have it here. Okay. Yep, right here.
3FFH.
Down here somewhere.
Try typing COM in /com.
Oh, we can there.
Here it is.
Okay. So can we find COM1 somewhere? I think COM1 is down there somewhere. It's actually kind of counterintuitive. Ah!
Nice baby.
I don't know about that.
Seriously, type /com.
There we go. First serial port. Okay, so we have I/O locations here. Look at this one here, okay? 3F0 to 3FF. It seems like an address, okay? But it does not correspond to memory address 3F0 to 3FF. In other words, if you look at memory for your PC as one big, huge, binder that has 4 billion pages, this is another binder. Your PC has 2 binders. One binder corresponds to memory, okay? Location 0, location 1, location 2, all the way up to 4 billion and whatnot, okay, depending on the size of memory. Then you have another binder that is corresponding to what we call I/O space, okay? And locations in the I/O space are basically called as what? I/O locations, okay? It's not very inventive. Each I/O location may correspond to a particular I/O device. So in this case, COM1, the first serial port on older computers, will use up certain addresses in the I/O space from 3F0 to and the next 8 locations or so. Okay? So what are we going to do with those locations? Well, those locations store something that is really interesting. For instance, one location may specify the baud rate. Okay, how fast is the serial line going? Another location may specify, okay, how many data bits do we have? How many stop bits do we have? How many parity bits do we have? So all of these things that you normally have to specify when you want to talk to a modem back in the good old days, they all have to have corresponding byte locations in I/O space. So every time you want to change the baud rate to talk to a modem, you have to change one of these locations accordingly. And that's how your computer, that's how your processor can talk to the I/O devices, the input-output devices. Now, the USB hub device also has its own location in the I/O space. I don't know exactly where it is located because I think that part can also be relocated. All modern devices can remap the I/O locations, but they have corresponding locations for the USB bus. Your SATA bus, same thing. It has locations in the I/O space to correspond to the various functions and the various bits to configure the SATA bus. Is that making sense? Kind of? Okay, so these locations are not really corresponding to memory. If you write a byte, a certain content to a location, don't expect to read back the same content, because each location here is a portal to an actual device. Okay, it changes the behavior of an I/O device when you write to it. When you read from that location, you're reading back the status of some sort of I/O device. And they may not be the same. When what you write to that location may not be what you're reading back, because it is a portal, it's a window into an entirely different device. It is not memory. Are we doing okay in terms of concept of input-output space? Okay. So with the Intel architecture, this space is entirely separated from memory. What that means is we have one set of instructions to access memory. Okay, we have the move instruction that can move from register to memory location and so on and so forth. But the move instruction cannot touch the I/O space at all. Okay, we have another set of instructions specifically only to deal with the I/O space. Are we doing okay so far? We have two sets of instructions, one set to deal with memory space and one other set to deal with I/O space. That's what we call an I/O mapped scheme, okay, because we have two spaces. That's the Intel way. Yep.
So does the I/O devices have an effect on like the processes, the data transfers? Like how
Does it have
fast
an effect on?
How fast it's processing?
Potentially, but usually no. Okay, the I/O space is really used to communicate with I/O devices, and on a regular computer, you have a lot of I/O devices, right? You have your network card, you have your USB, device, you have your. Most computers do have a keyboard, a PS2, connector, so that maps to another I/O device location. You have your graphics card. Okay, the graphics card is kind of like a special case. It may have something like that. Sound cards have their own I/O locations. What else? Have I/O locations. Anything on at the south bridge, your mouse pad, but that's USB also. That's everything are connected to the USB these days. The power button. That's
Power
audio.
port.
The power port. I don't know. It
Raises an ACPI event.
Okay. But most devices now are USB, so we are consolidating all the I/O devices to just USB, PCI Express, SATA, and just a few these days. Okay.
TPM. TPM.
TPM.
Your trusted platform module. It stores your cryptographic keys so that companies can lock you out of your own media.
Yes, great. Excellent. Okay, so the other scheme is called memory mapped I/O, which is not how Intel does it, okay? What this means is in the memory space, remember the logical memory space, that can be really huge? We are basically saying that in software, we can carve out a section of this memory space and say, okay, let me go find my pen here. Okay, the MMU on these particular computers can carve out a particular section in memory space. In other words, with memory mapped I/O, there's one single binder, except certain pages of that binder are special. So in this case, let's just say that we carve out this section here, and now whatever is in the red portion here is no longer mapped to a memory chip. Okay? When I try to access locations in in this particular region, they are all corresponding to some registers of I/O devices. And as a result, in a memory mapped I/O scheme, you only have one set of instructions to deal with memory locations. The same set of instructions will also be responsible to deal with I/O input-output devices. Yep.
Does MMU have to keep track of that? Or is
Yes,
that
the
just-
MMU is responsible to keep track of which portion of logical memory is mapped to what. But a part of that is also implemented off-chip. In other words, there will be another chip, peripheral chip, sitting outside of the MMU to basically say, okay, now that will be like the main coordinator to coordinate and say, okay, I/O chip, blah blah blah. Somebody wants to talk to you. Are there any other questions regarding memory mapped I/O? We can't really do a whole lot of experiments in this class regarding I/O operations. Yep.
What does use it, not Intel?
Sorry.
What does use memory mapped I/O, not Intel?
The AVR architecture uses that. The Motorola 68000 architecture uses that. Just about any architecture that's not have a separate instruction set to deal with I/O space, they all have to be memory mapped. And essentially all non-Intel 386 type processors are memory mapped. Yep.
Is there an advantage for doing it that way instead of?
Oh yes, because the number of instructions will be smaller. You don't need a separate set of instructions to deal with I/O locations. It will be the same set of instructions that you normally have to use to access memory. And that's why most RISC architectures are memory mapped. Because remember, what does RISC stand for? Reduced instruction set computer, right? So this is one way to reduce the instruction set because you only have one set of instructions to deal with both input-output as well as memory access. And what is the 386 architecture? Is it a RISC?
No.
Nope, it is a CISC. It is a complex instruction set computer, and that's why they have a huge instruction set, and they can allocate certain instructions just to deal with input-output. But a lot of that is just for backward compatibility. In other words, even if Intel wants to go back and say, oh, this is not a good way to do things, they cannot change it because there are so many programs already compiled with only the binary that backward compatibility becomes a big issue with Intel architectures, which was actually part of the reason why we had the PowerPC architecture. Do you guys know about the PowerPC architecture? What was the original purpose of the PowerPC architecture? The PowerPC architecture is a RISC type architecture which was co-developed by Motorola, Apple, and I think IBM was a part of that too. Okay? And a part of that was basically Apple trying to say, okay, we don't want to use the 68,000 processor anymore, and we want to make computers that can run programs that were compiled for the 68,000 architecture. In other words, emulation. The same thing that you are doing with QEMU. But this is a cross-architecture emulation. In other words, you are using the PowerPC architecture to pretend and execute instructions that are intended for the 68,000 architecture. IBM came along and say, oh, we want something like that too, except we don't want to emulate 68,000 instruction set. We want to emulate, guess what? The Intel x86 architecture. So Motorola came up with an architecture called the PowerPC architecture that actually has specialized hardware features to make the instruction emulation far more effective. I think it's a jump table kind of mechanism. But it does have acceleration technique to make emulation faster. Because Motorola is saying, okay, so now I can sell the same processor to both IBM and Apple. Apple can make their computer backward compatible to their old 68,000 architectures, and IBM can make their architecture backward compatible to their Intel architectures. Okay? Except things did not quite turn out that way. And then the PowerPC found its way into what these days?
Macintosh.
It's the Macintosh, but not
Older
the recent Macintosh. This was a big thing. This was a big thing. I'm hoping that you guys at least know about it, have heard about it.
The Android.
The PS3. Okay, the PlayStation 3 has what they call a cell processor, which is based on the PowerPC architecture. Okay, now what did Sony do recently?
They tried to hot arrested for reverse engineering to re-add features that Sony removed from its original product shipping.
Yes. Okay, so PS3 originally has the ability to run a third-party operating system, something other than what Sony wants you to run. So originally it has that capability, which was what the U.S. Air Force, the Cyber War Division, was using a whole big network of PS3s to string them all into one single big supercomputer. And then later on, Sony came around and say, okay, we'll update your BIOS and your firmware, but after this update, guess what? You cannot run a third-party operating system anymore. So it was trying to lock out people from using a third-party operating system. Somebody found a way to get around it, okay? And that person obviously disclosed the solution to the whole world, and people are now saying, oh, cool, I can run Linux again on my PS3. So Sony came around and said, oh, but you just did something to circumvent copy protection or a certain type of protection mechanism, and therefore it is a violation of the DMCA, the Digital Millennium Copyright Act. And did that guy actually get arrested and thrown into jail?
He's arrested in jail now, and he's roomed up with Bubba, last I heard. Not having fun.
Not having fun.
No.
Yep. But one student in one of my other class told me, how the hack was possible. Okay, I'm not sure whether you guys have heard of that. It's a random generator function that returned a constant of 4. And that was done at a chip level. In other words, there's no way Sony can actually fix that problem with firmware update. Whatever they update, once people discover this particular hack, there's no way to fix it. They will actually have to fix the hardware in order to fix that original problem. Yep.
What they've decided to do instead is to require online activation and product keys.
And hire more lawyers too. They can fix anything.
Throw enough lawyers at it and you don't have to worry about your soul.
I think you have to throw away your soul first to hire more lawyer. Chicken and egg. Okay, so that's it for today's class. Please read, all we have, read up to this point, because next time, okay, don't go yet because okay, you guys really need to read ahead of me because next time on Thursday, we will actually start to write assembly language programs. So you want to read ahead read ahead of me as much as you can because you will have homework assignments next time that has programming in it. You guys have been waiting for that.
Finally. You're going to stop the recording?
Oh yeah, I can stop recording. You got something to say?